Hi everyone, this is our last unit. We're combining Unit 8 and 9 into one unit. So make sure you get this link from Canvas, click on Unit 8, download it, and next to today's date. This warm-up here is a review of Unit 3 because our AP exam is coming up in a few weeks, and so we want to start reviewing now through our warm-ups as well. So go ahead and give it a shot. You can pause the video while you try it and then unpause when you're ready to see the answer. All right, so this is about experiments. Unit 3 was collecting data. And we've been using a lot of the stuff from Unit 3, we just haven't really realized it. One thing I want to remind you is that an experiment imposes treatments. So that's going to be the main keyword that you want to use when you determine if something is an experiment or not. And then the explanatory variable is like your independent variable, and the response is your dependent. So I'll just remind you of that. So he manipulated the brightness levels, which means that was our explanatory, and he measured, where does it say that? He measures the amount of time till the battery is dead. So that's a response. For letter C, random sample and random assignment are simple. Now, this is why we have the random condition. And so remember, I'm gonna remind you of why we even check the random condition. We wanna be able to do one of these two things with every inference procedure that we do. And so a random sample means that we can infer about the population. And that means we can apply what we learned to the population. And then random assignment means we can establish cause and effect. And so this guy did both, which means we do know that a high brightness on your iPhone causes the battery to die faster. And so that's the goal of inference. And it's why we have a random condition. So not all problems we do meet both criteria of a random sample and a random assignment, but we're looking for at least one so that we can establish some sort of, so that what our study is useful to either the population or cause and effect, and then hopefully we can study more and do both eventually. All right, so hopefully that was a nice review of Unit 3, and now we will move on to the packet that says which color is the most common M&M. So take that out. Now, hopefully we're at school or you've got some M&Ms at home, and what I want you to do is just take a pack of M&Ms, a little pack, a mini small kids pack or whatever, snack pack, whatever they call them, fun size pack, and count the number of each color. And then there's going to be a Google form that isn't available yet, but whoever is leading this lesson will put the Google form either in the chat or on the board for you to fill out here. And you will fill out the number that you got for each so that we can tally them up as a class and use that as our class data. So after you submit the Google form, then you're free to eat your M&Ms. Now, if we're in class, then the teacher will pause here to give you guys the data from the Google form. So we'll be wanting to total up each of the amounts from brown, yellow, orange, green, blue, and red that you guys entered into your Google form. I've done this before with another class, so we're going to use that data as an example. Remember, you should have your own data if you're in class, but some of this stuff will still apply if you're not, for both groups, in class or not. So first of all, I'll show you what we got when I did this before. We had 78 browns, 90 yellows, 127 orange, 145 green, 105 blue, and 62 red for a total of 607 M&Ms. So this is our sample size. Now, for the HO and HA, what we're doing is we're still doing significance tests, but this is a different kind because we have, if you look at this little box, we have 1, 2, 3, 4, 5, 6 different proportions. We've only ever done 2. So we've done a 1 proportion z-test and a 2 proportion z-test, but now we have 6. So what I'm going to do is list them all out. P of B for brown equals 0.13. We want them to be decimals. P of Y for yellow is 0.14. P of O for orange is 0.16. P of G, 0.24. P of blue, oh no, I can't read. I missed one. 13% brown, 14% yellow, 20% orange. Sorry about that. 16% green. I have blue, I'm going to do BL since I already did B for brown, is 0.24. And P of R for red is 0.13. So these should add to 1 because this is all of the M&M colors. So when we've done 2 proportion z-tests before, they did not add to 1. There was 2 separate groups. This is 1 group with a hypothesized distribution of 6 different proportions. And so our alternative is just going to be at least 1. Sometimes people will say 2 or 2. That's the same thing. Is different. So what that means is the reason I write 1 or 2 is because if one of them is different, let's say the green isn't really 0.16, then that 0.16 has got to, if it decreases or increases, that change has got to be reflected in another one of the proportions too. And if you guys are in AP Bio, you have probably already done chi-square tests. And so hopefully this is familiar to you. We don't do it as much with the ratios for the different characteristics and stuff are part of the nature, but we do it with specific proportions like this, or we do it with even distributions a lot. So we'll look at a couple different examples today. Now I'm only going to do one more question with you. Let's suppose the M&M's claim distribution is correct. Remember, that's always how we do a hypothesis test, is we assume that the null proportions are true. And if they are, we can determine how many we expect of each from our sample. So I had 607 in the sample, and I expect 13% of them to be brown. So what I'm going to do is find 13% of 607 by just multiplying 607 times 0.13. And I get a 78.91. I want you to write the decimal this time. So make sure you write decimals. It's tricky because in our other units, we've rounded these up for expected counts. In other times, we've calculated them. But here we do not want to because we're going to be operating with these numbers. So we have 84.98. Orange. 97.12. Oh, wow, why can't I do orange right? Orange is 0.2. 121.4 is what I meant. Green, 97.12. Blue, 145.62. I can't read. And red, another 78.91. Because it's also same percent, 13% as the brown. Okay, so I'm just going to remind you about each of those. That was 607 times 0.14, 607 times 0.2, 607 times 0.16 times 0.24, and 607 times 0.13. So those are our expected. Now on the next page, or the next box, you're going to be using these expected in their entirety as decimals to do some operating. So you're just going to be filling in the rest of the box of the table with all of these things: observed, expected, observed minus expected, and then you're going to square them and then divide by the expected. So these are our observed values at number 1, and we have our expected in number 2, and etc. So you're going to go ahead and do the rest of this page. So pause here, finish through 6, and then we'll come back together to debrief, take some notes, and try to check your understanding. Okay, we're going to go ahead and start the debrief here. So I'll stay on this page. And what we just did was called a chi-squared goodness of fit test. And so I'm going to write that right here. So it's called chi-squared goodness of fit test. And we do these when we have one hypothesized distribution, we have one sample. I'm going to call this sample data, or the observed values. And it gives us one sample. And then we have proportions listed. So for your HO, you just list the claimed proportions. I'll put HO like this so you don't have to use a backwards arrow like me there. And then for your HA, we say at least 1 or 2, both are correct, is different. And then we will move on to number 3. These are our expected counts. We have a formula for it. So the expected counts formula that we use, notice what we did was we took each sample, for each one we took the sample size n of 607 and then multiplied it by each proportion from the null. So a P with a little I stands for each proportion. And the rule is that all expected values should be at least 5. And so do not round them. Okay, so you always want to calculate, show your work, and label the expected counts for a problem with chi-squared test. All right, next we have this whole table that we filled in, and that was just a lot of work to get to the final answer, which is the chi-squared test statistic. And so the formula for that is going to be chi-squared, this is a Greek letter, C-H-I, chi square like that, but we like to use just this Greek letter for it. So it is the observed minus the expected, and then we squared it all over the expected, and then what we did to get 39 was to add up all the values. Remember, this table is going to vary depending on what you got in class. So this is just an example, but you should have done the same operations, and the formula works out the same. And so number 4 and 5 are just talking about what would happen if we had a really small, what value will we get if our observed were very close to our expected? Well, observed minus expected, if the two numbers are really similar, then that would equal about 0. If the two numbers are really different, then when we subtract them and square it, we get really large numbers. So here's an example. Here's where Brown, look, we had 78 observed and 78.91 expected. So that's very close. So that component, these are called components. That component was really close to 0. And so we can see that this one is the furthest from the expected because it's got the largest component relative to what we expected it to be. Now, blue was pretty far away as well. Both were, one was 47.88, one was 40.68 away, but the green had a larger impact because we expected fewer of them. And then we have the same 3 conditions we've been doing. but I'm going to add something to the large counts. We're going to say all expected counts. And because there's so many expected counts sometimes, it's unreasonable to expect them always to be at least 10, like we've done with our proportion test. Now we want them to be at least 5. And so this formula is that n times pi should be at least 5. Notice the difference, 5, not 10, and then that this is not normal. So a chi-square distribution, I'm going to teach you a little bit about that right here, is skewed to the right. And so let's see, skewed right. It starts at usually 0. It's always positive. At least. And then we have the DF. There's the degrees of freedom, and it's the number of categories minus 1. So in this particular problem, we had, let's see, 6 different colors, blue, yep, 6 categories minus 1 is 5. So I would draw this. The peak is at the DF minus 2, so that would be at 3. And so we have 0, 1, 2, 3. And then our chi-square 39 is like way out here, 39.1543. So I'm going to show you how to get the p-value. We have 2 ways to get it. So one way is to use table C. We have a table C now. And so our DF, like I said, was 5. The categories minus 1. So we'll just make that note here in red on the table because you have this yellow paper. And so I'm looking at row 5. Let's see. And in this row, we got a chi-square of 39. And this is after 0.0005. So that means that our p-value for this problem is less than 0.0005 from the table. That's all I can get from the table. But I could also use, of course, a CDF in the calculator. So I'm going to show you that. We have second vars. We're looking for chi-square CDF. See, it's number 8 right there. Our lower is always the chi-square, which was 39.1543 for my class I've already done. This might be different for your class. Our upper is the infinity, so I just put a bunch of 9s. And the DF is the categories minus 1, so 5. And I get 2.21 times 10 to the negative 7, which is in fact less than 0.005. Because that would have 6 zeros. So that gets you the exact. The table will get you an interval estimate. Okay, so here are the notes on the chi-square distribution I've talked a lot about this, so I'm not going to talk really very much right now. I want you to go ahead and pause this video to copy it down, and then we will look at the check your understanding. You can give it a try after you take the notes, but if you want to wait and see how I go over it, then that's fine too. You can wait, either one. Okay, so the check your understanding is a little bit different because what it says is the hypothesized distribution is each side was equally likely to show up. So I'm going to label that as the hypothesized distribution. So our null is that they are equally likely. Remember, the null is always no change or whatever. And so in this case, I just listed them out that the outcomes are all going to equal each other and that they will also equal 1/6. Because that's what equally likely means on a 6-sided die. And then for all alternative, we could say at least one. You can also say or two of the p's are different, and then you need to define the p. So you have to do that. And so it's a proportion. These are proportion problems, so true proportion of rows on each side. Now the expected count is your n times each p. So I have 90 rolls and each p was 1/6. So that's where I got that. There's going to be 15 rolls of each number. All expected are the same, because that's what equally likely means. So expect all 6 of them to be the same. You could also just take your sample size and divide by the number of categories for a problem like this. So 90 divided by 6 is 15 as well. The formula, you need to show the first, second, and last for credit. And so that's what I did. Die 1, 2, and 6. The degrees of freedom is your sample size minus 1. And then I used the p-value from the calculator to do it, but the table C would have given you an interval. Now I do want to show you a little bit more about the calculator because there's more you can do here. So everyone get out your calculator and hit stat enter. And so for this problem, we can use our lists. They're very helpful in organizing all of the numbers that we have. So first thing I can do in my L1 is put the observed. And I'm gonna write this down for us while we go. So when I show this screen again, you'll see it. So I'm gonna put 12, 28, 12, 13, 10, 15. And we can kind of see that it looks like 2 came up way more than we expected, because that is the one that's the most, and we expect it to be equally likely. Then for our L2, we put our expected, and in this case, that was 90 divided by 6. And if I expect them all to be the same, I'm going to put 15 for all 6 values. Remember, equally likely means they should be the same. So you put your expected there. Now in my L3, I can make it do the math for me. Hit a parentheses. And the formula is observed, so second number 1, minus expected, so second number 2, squared over the expected, so second number 2. Don't forget the squared. You should never have negatives in this column because the squaring makes them go away. And then don't forget the parentheses. So it should look exactly like my screen. Make sure L3 is highlighted, not these lines. That won't work either. So hit enter, and these are our components. So I'm going to write that on my paper. You can copy it when I show the screen again. And these are the components. So now I want to add this list up. And so I can go home, second quit. It takes me to the home screen. I'm going to hit second stat math 5. And I want to sum list 3 where all the components are. So that was how I get 14.4. So I'll write that down. Okay, so I wrote everything down for you right here. You can pause here to write it down to make sure you get it, and that's how you can get your chi-squared a little faster. There's an even faster way, but we'll show you that another time. All right. So with that, I got the chi-squared CDF, so second bars, number 8 here. I can put in my 14.4. Upper is always 9 to 99. DF is categories minus 1. There were 6 categories, so 5, and I got 0.0133 like I had written down. So hopefully that was helpful. And then, of course, we'll learn how to apply the pass process to this next class, and some more practice with it and AP FRQ rubrics. So I hope you guys have a great day. You may finish copying down anything you missed here and go do your homework in Sapling. Thank you so much. See you next time.